Good evening, class. We are looking at Chapter 6, Applications of Integration, Section 6.4, Work. This session is being recorded, so please, if there is any issue regarding privacy, make sure not to participate at all. Make sure your audio video is muted, nothing on the chat. You can even change your name to your initials. All right. So 6.4. Work is going to get started. So let me put this in slide mode, and then in a couple of minutes, right now I turn off the video because I've had a little bit of an issue with the internet. Please check and recheck. If by any chance it gets blurry, let me know. Okay, class? Your screen. So, okay, so this is the synopsis of what you need to know. We looked at the area of the region between two curves, and I've told you the way I approach it is very simple. I would write an increment of an area is h times dh. You draw an increment, either it's a vertical strip or a horizontal strip. You find the height, you find the width, which is normally dx or dy, and then the result will be the y of the top minus y of the bottom, okay, times dx, or x of the right minus x of the left times dy. That's how you get that. The method of slicing, when you want to find the volume of revolution, okay, you revolve it about a specific, axis. Okay, could be the x-axis, could be the y-axis, or could be any line. X equals this, y equals that. Now we have an increment of a volume. I'm going to call it dV, which is the area times dh. The area is area of the disk. The disk gives you the area in the form of a circle, so it's pi r squared. dH is the thickness of that, which gives rise to its volume. Okay, that is obviously either dx or dy. And then all you have to do, just figure out what is r. Normally, as far as the definition, r is the distance from the axis of rotation, distance from the axis of rotation. Okay. Many times it just becomes f of x, but in any event, you have to figure out what r is, and in some cases we end up with a washer, becomes r pi times r out squared minus r in squared. You've seen those. And also we looked at the cylindrical shell. Okay, instead of dealing with the disk, you peel off, if you will, just like peeling off a potato, if you will. So it's just the peel off that gives rise to the shape, which is really the lateral area, okay, the surface area without the top and the bottom, okay, the lateral area of a cylindrical shape. And if you multiply, which is simply 2 pi r times h. If you multiply by its thickness, which is either dx or dy, which I'm going to call dr because it goes back to r, then you have a method of shell. All right. Now we're going to look at applications 6.4 work. So integrals as net change. I hope you remember one of the Newton's law, the Newton's law of motion, F equals ma. F is the force, m is the mass, a is the acceleration. Everybody remembers that, okay? So that's and Newton's law. And if it has got to do with the gravitational force, it changes to mg. Everybody remembers that, with the g force of like 9.8 meter per square second or 32.2 feet per square second, depending on the units. As far as the work is concerned, work is the product of force and distance. So when we multiply the force, okay, then by the distance, we get Fd, or the work. Now, by the way, when we say force, understand the weight is the force, mg, okay? And we need the m and we need the g, and m is the mass, by the way. And that's the formula that we use in, SI unit metric system. But the old British system takes M in essence and the force to be the same, okay? Basically, if you want to calculate the work, it's very simple. Multiply the two as long as the force is constant, okay? When it's not, it's a different story, okay? So when the force is constant, it makes it easy to calculate. One of the things that we have dealt with, in the case of a spring, the Hooke's law for a spring says capital F equals K times X, where K is called the spring constant, okay? So remember, the force in metric system is the product of the mass and acceleration and has the units N Newton, okay? Okay. Mass has the units kilograms, okay? Acceleration, meter per square second, okay? As far as the units are concerned, okay? So if force has the units Newton, okay, and X is in meters, then K must be Newton divided by M. I hope you see why this is the case. Everything we do to numbers, we do to units. This is just refreshing your memory about some basic physics everybody has had, I hope. If not, so be it, I'm just basically going over that. All right, so let's look at a very simple example. We want to see how much work is done, okay, if a 200 kilogram rock is lifted to a height of 3 meters, which means we are using this formula. W equals F times D, and F is MA. Because we are lifting up, instead of MA, we're going to use MG. Class, one more time. W is F times D. Instead of F, we use MA. Because you're dealing with the weight, then instead of A is the same as G, remember that. G is the acceleration due to the gravitational force. Just plug in, okay? M is 200. G is 9.8 meter per square second, roughly, and the height is given, 3 meters. So 200 times 9.8 meter per square second times 3 meters, and it becomes this unit. Take a look, okay? Everything we do to numbers, class, everything we do to numbers, we do to units. I'm just refreshing your memory about some of the basic formulas and units in physics. So kilograms, okay, times meters becomes meters squared divided by S squared. Or we can call this J, which stands for joules, everybody, okay? So, and here's the definition of a joule. 1 joule is, okay, so this is 1. If this is 1 joule, okay, I'm showing you the product of F, which is in Newton, and distance, which is in meters. So whatever we do to numbers, we do to units. So the formulas follow. And so therefore, we are saying that in SI system, 1 joule is the same as 1 Newton times 1 meter. Okay, or this one. By the way, let me just cross this. And so you get that. So joule, unit of work or energy in the International System of Units, SI or metric system, it is equal to the work done by a force of 1 Newton when its point of application moves 1 meter in the direction of action of the force, okay? And it's named after the English physicist. It's equal 10 to the power of 7 ergs. And if you want to know what that is, if instead of kilograms, you go with grams, and instead of meters, you go with centimeters, that's what you get. And by the way, I hope you remember, kilo means 1,000. So 1 kilogram is 1,000 meters, and 1,000 grams, and 1 meter is 100 centimeters. These are all basic units conversions everybody knows. So, all right. Now what happens is that over a short distance, if we have a small distance, okay, even if the force is not constant, we can assume it's constant, just like what we did with the area, just like what we did with the volume. So an increment of work will be capital F of x times d of x. I hope everybody remembers the concept from the area and the volume, okay? And if we add them up, it gives us the Riemann sum, and it becomes the integral of a to b f of x dx. And that's how work is calculated, where this function is the force function. So again, if the force is constant, you multiply it by d distance and you're done. But if the force is a variable force, it changes, then you have to go with the integration. All right, let's start with a couple of examples. Again, I put the definition of joules for you here again, so just so you have it. All right. We are given this example. What is the force on the bottom of the aquarium? This fish tank, we want to see what it is, okay? And the force, by the way, I remind you, force is equals m times a or m times g. Even the weight is a force, and work is the product of the two. So according to this, we have units in old British system, okay? Now, we need to know a couple of things. So everybody remembers that rho equals m over v, and m is rho times v. Rho is the density. I hope you remember all of this stuff from physics. Rho, density is defined as total mass over the total volume. So if I do the cross product for this fraction, mass becomes the product of rho, the density, and v, the volume, okay? Now the density for water, and again, that comes, this is a piece of information from physics, it should be provided to you. It's 1,000 kilograms per cubic meters. What does it mean? That means 1 cubic meter of water weighs 1,000 kilograms, okay? It has a mass of 1,000 kilograms, okay? So I want to make sure we understand what this means. When we say rho is 1,000 kilogram per cubic meters, that means 1 cubic meter of water has a mass of 1,000 kilograms. Now, in old British system, it translates to 62.5 pound per cubic feet. Now, the way the pound works, see, kilograms in a metric system is the units of mass, not the force, okay? So if you want the weight in metric system equals mg, so this has to be multiplied by g, 9.8 meter per square second. That's not how it works. In the old British system, they keep this as the weight also. So with that being the case, okay, we obviously can see that the volume here is 2 times 3 times 1, right? Let me write that. The volume is length times the width times the height, right, everybody? So we have the volume. So we can find the force or the weight using this formula. So what is the volume? 1 times 3 times 2, in any order you want to put that, the length times the width times the height. And then you're going to multiply by the 62.5, which is given here. And now you have the answer. You just come up with the answer. Okay. All right. Now, what about the second part? So basically, the first part, you multiply all of those numbers. In other words, I am using this formula here, class, okay? What about part B? You have to multiply by 10 feet. The work is the amount of force times the height. There you have it. Okay, everybody? So I hope everybody is comfortable with that. Let's move on. All right. The way we write the units for this one is just pounds. Okay. Is it in pounds? It's in foot. So we say foot pound. Foot pound. Okay, foot pound. That's how you write it. I hope everybody is okay with that. Okay, excuse me. So the units are different, class. The units are different. All right, let's look at another example. It takes 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done stretching the spring to 4 meters beyond its natural length? We are using Hooke's law, okay? F equals K times X, and the work is the integral of A to B f of X dx. So all you have to do, come up with f of X and plug it in. But in order for you to come up with f of X, you need to figure out what K is. And so the piece of information here is that 10 newtons, F being 10, it can move this by 2, so that basically means F is 10, okay? And K is missing, and X is 2. That's the meaning of it, okay? So that means 10 Newton can move it in this fashion. So using F equals Kx, so if you want, you can write, this is F, and this is X. You are going to find the K first. So just plug in, and you find K to be 5, which means the formula, the general formula, F equals Kx becomes F equals 5x. Now the second part says, okay, how much work is done stretching the spring to 4 meters beyond its natural length? Okay, and that follows the formula that we have. Beyond the natural length by how much? 4 meters. So A is 0, and you're going to go from 0 to 4, everybody. You're going to go from 0 to 4. You're going to go from 0 to 4. Why? 4, because we want to move it 4 meters beyond its natural length. Okay, we want to stretch it that way. And so f of x is 5x, okay? And dw is f of x times dx. This requires the integral simply because the force is not constant. Class, why is it the force is not constant? Think about it. You have a spring, and the way you stretch it, okay? When you start stretching, maybe you need a little bit of a force. As you keep on stretching, you need more and more and more force, okay? It becomes harder and harder to do that. So the force of stretching is not constant. The force of stretching is variable. And basically, you put the 5x into the integral of a to b, where a is 0 and b is 4, and there you have it. Okay, class? Okay. Now you just do the math, and it becomes 5 halves x squared from 0 to 4. Replace the x with 4. Square it becomes 16. Divided by 2 becomes 8. 8 times 5 becomes 40. And joules or Newton meters. Joules or Newton meters. Again, I think it's pretty straightforward, class. Okay. I hope everybody is okay with this. And so we end up with 40 joules, also known as Newton meters. Okay. All right, let's go to the next example, the type of example again that I think by now we should be familiar with, dealing with more examples involving Hooke's law. A spring has a natural length of 1 meter. So L, if you will, sometimes they call it, the natural length of 1 meter. A force of 24 newtons can stretch it to 1.8. Okay. Now what we want really is to come up with the equation for this. Okay, so in part A, they're asking for the formula for F equals Kx. Now, it is important to know that it is the change, this X, in physics, when we looked at this concept, the formula was as follows, class. F equals K delta X. I don't know if anybody remembers that. Okay, anybody has studied it in physics. The reason they use delta X, because delta X refer to the change in X. In essence, it's not the dx and delta X we use in differentiation. And because we didn't want to mix them up, we used X. So in calculus, we use X, which is really delta X in physics, and what it refers to, the change in natural length. So what is the natural length? 1 meter. If it's 1 meter, we are in good shape. But when it changes to 1.8, now the difference between the two is 0.8, everybody. Okay, we want to find the equation. Okay. Therefore, it's important to see that you have a change of 0.8, not 1.8, everybody. We are going from 1 to 1.8. I hope everybody can see what's happening. Okay, so in other words, if this is normal, 1 meter. So now, normally it's 1 meter. We have stretched it hard enough to go to 1.8. What matters is the difference between the two, okay? I can't emphasize this enough. So F equals Kx, that's the formula we use, but remember in physics is delta X, the change is 0.8 in this case, okay? (24), okay? So 24 divided by 0.8 and K becomes 30. Therefore, the formula F equals 30X. Okay, everybody? So 24, not Tony. 24. All right, in part B, we are going to see how much work is needed to stretch the spring 3 meters beyond its natural length. That means, in essence, from 0 to 3. So we are going to use the integral of the same thing from 0 to 3. And as you know by now, of course, this is a very basic integration. You know how to do that. So it's 15x squared from 0 to 3. Replace the x with 3, becomes 9 squared. You multiply it by 15, you get 135. And anytime you're dealing with applications, make sure you put the proper units. I can't emphasize this enough. So in physics, units is a must. Okay, so put the proper units, everybody. Put the proper units. All right. I think we are okay with this, so we can move on. We are okay. Here's the next one. If the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pounds, how much work is needed to stretch it 9 inches beyond its natural length? And to do that, the very first thing, class, your first step is to find this, class. You have to find this. So there is enough information for you to find F equals Kx. So basically, you need to find K. That if K is missing, okay? I hope everybody is okay with the concept that I'm referring to. So we need to find the value of K. Okay, everybody? We need to find the value of K first, which means we are going to do what? Let's go through the process and see what needs to be done. We can easily come up with the answer. So how much work, and again, the formula is W equals the integral of a to b f of x dx. So that means if we are going to go 1 foot beyond, that means this is from 0 to 1. Again, we are using, in this case, the old British system. So the integral of a to b becomes the integral of 0 to 1 f of x dx, okay? And we are going to use kx dx, and that is equal to this number, which means we work it out and we find the k. So the very first step is to find the k. In other words, you would say A is 0, B equals 1, W equals 12, put the two concepts together and find K. So that's what we are going to do. Okay, everybody. We want to find K. The value of K is missing. So this is the way to do that. And so this is 1/2 K x squared from 0 to 1. Replace the x with 1. You get basically K over 2. And the 0 gives you 0. So K becomes 24, which gives us F equals 24x. So that's the first part, finding K. So the first part we found K. Now we are actually making this to be sort of part B. How much work is needed to stretch the spring? 9 inches. Well, the very first thing is 9 over 12, because you have to go with the proper units. 9 over 12, okay? So F is 24x. F is 24x, class. I thought I mentioned that, but I didn't put it. F equals 24x. So we have that. Now, the next part is for part B to do the math and pay attention to the units that you're going to use. 9 inches is 3/4 of a foot. Why is that important? Because the units that are used here are not inches, okay, class? Are not inches. Foot pound, remember that. For example, this was foot pound, okay? Foot pound, 1 foot. So 9 inches must be changed accordingly. Okay, so now that we know that, we just basically do the math from 0 to 3/4. Okay, everybody? So we find that. Now 24x, the integration becomes 12x squared from 0 to 3/4. You plug in 3/4 and square it, which becomes 9 over 16 times 12, and it becomes 27 over 4 precisely. As I mentioned, in calculus, you want to stick with the precise answer, class, just to be on the safe side, and you don't want to take a chance, okay? Stick with the precise answer. Stick with the precise answer, everybody. Okay. Okay. So 27 over 4. Of course, in this case, even if you change it to a decimal, it's precise because 27 divided by 4 becomes 6 3/4, which is 6.75. But in some cases, if it's, if it has in the, many decimals, you got to be careful with the number of decimals you use. Okay, here's another one, and here's the basically we have overkilled it. I think I'm going to look at one more example just quickly. We are going to look at one more example of the Hooke's law, and then we change gears. So according to this, we need 6 joules of work. So we are going back to SI or metric system class. We are going back to metric system. If 6 joules of work is required to stretch a spring from 10 centimeters to 12 centimeters. And another 10 joules is going to take us from 12 to 14. Okay. What is the natural length of this spring? Okay, so we don't know the natural length. And remember, in this formula, when we stretch it beyond the natural length is what matters. So what is the natural length? Using, first of all, this stuff, we don't know. And we're going to say, okay, we don't know. Let's say L. Okay, class? If the natural length is L, so what happens is that, first of all, 10 centimeters. Okay, let's just change that. To 0.1 meters. 0.12 meters. Just in case, so you know, if you don't change it and you keep it as 10 and 12, the reason it will work because the top and the bottom are both using the same units, even if the units are off. Because they are using the same unit, it does work. But anyways, so we are using this formula, everybody. Okay, kx dx, and that's what we have. So 6 joules needed to go from 10 to 12 centimeters. 10 joules needed to go from 12 to 14. So what do we mean by these two now? Let me just give them numbers because I want to make sure you understand what I'm really trying to do here. If I call this equation number 1 and I call this equation number 2, what are we dealing with? We are dealing with a system of equations. In fact, system of nonlinear equations. System of equations. What does it mean? That means we have 2 equations and 2 variables. What are the variables? L and K. What about X? It becomes clear that X you plug in, so X is not missing in essence. In both cases, we get 1/2 kx squared, 1/2 kx squared. So the first one becomes 6, and now you plug in the upper, I put UL, upper limit. Let me just write it out for you. Okay, upper limit. And obviously, lower limit. Why did I do that? Because I didn't want to write this 2 times and write this time. This one 2 times. So use this formula, put this as upper limit, this as lower limit for the first equation. Put this as upper limit, this as lower limit for the second equation. So this is the first equation, everybody. And the second equation. Now, of course, you're going to get rid of 1/2. That means you multiply by 2. This becomes 12. Let's just quickly show you that one. So you get rid of 1/2, and this becomes 12. You get rid of 1/2. This becomes 12. In other words, you multiply both sides by 2. Okay, that's the first. Now, you really have to square this. I'm assuming you can do that. The same thing, work it out. The same thing, work it out. If you simplify it, I'm not going to spend time doing that. It does take a little bit of a time. If you do that, you end up with the following 2 equations. 12 equals k times this, and 20 is equal to k times that, okay? And you can subtract one from the other. Notice both of them have 0.04L with a negative sign, and k. So if you subtract one from the other, it doesn't matter which one, okay? So if we subtract the first one from the second one, we end up with this. I'm assuming you're a calculus student, you can follow this simple equation. Subtract. So when I say 2 minus 1, that means I'm subtracting the first line from the second. And K becomes 10,000 newtons per meter. Okay. What about the length? The natural length becomes 0.08 meters. So there are a couple of steps missing in between. I'm leaving them for you to handle. All right, let's look at a couple more examples quickly. A 180-pound cable is 60 feet long and hangs vertically from the top of a tall building. The reason they say tall, top of a tall building, that means it's, it covers the 60 feet class, okay? Otherwise, it has to mention to you, it doesn't, you know what I mean? A portion of it is hanging or it's on the ground. So top of a tall building, that means taller than 60. That's the idea, okay? How much work is required to lift the cable to the top of the building? And for part B, if we want to only pick up 25 feet of that. Okay, so let's go over a couple of interesting things. Okay, when you have a 180 pounds cable, 60 feet, okay, remember an increment of a cable, you have to know the density for that. The total mass divided by the volume, but in this case, we are interested in linear density. So again, the formula is rho equals m over v class. So 180 divided by 60 gives you 3 pounds per foot. This would be the general density. However, I want you to pay attention to the fact that this is really being changed to m over L as a linear density, meaning what? Meaning every foot of this cable is how many pounds? 3 pounds. You are assuming it's a linear one. You're assuming, the cable is the same all over. So every, if it's 60 feet and it's 180 pounds, every foot is 3 pounds. So that's important to know. This is the density, but I put the original formula for the density. I wanted to explain it here that it is the linear density. And the idea is that an increment of a length, delta x, is being raised up. So I want to explain what's happening here. And what is happening is that if you are dealing with a heavy cable and you're pulling up, think about this concept, class. The top of it, the very top, you don't have to really pull up. But if it's, let's say, 10 feet down, this has to go up by 10 feet. This has to go up by 20 feet. The bottom of the cable has to go up by 60 feet, which means, okay, at any given time, a portion of a cable left has to be pulled up. So for the sake of argument, if 2 feet is gone, 58 is left. So you have the weight of 58 feet. If 10 feet is up, 50 feet is down. So you have the weight of 50 feet. And that's important to understand. Okay, class? Okay, so that's why you really have to realize this is a variable force. So having said that, small piece of the cable of length dx pulls down with the force of 3 times dx. Okay, remember, that's why we calculate this. So 3 times dx pound, that would be a small increment, small piece of a cable. Okay. If we let x be the distance this piece has from the top of the building, so this piece has to be pulled up by x amount. Okay. Then what is an increment of work? Remember, work is the product of force and distance. So here's the force, we have to multiply it by a distance. So dW is the force times dx, and the amount of force we said is 3dx, and the amount of distance we said it's x, so it's 3x dx. Now, of course, foot-pound, but that's the unit. So I hope you realize what we are doing here. We are establishing this, okay, class, and we're going to go from A to B. We are going to go all the way up from 0 to 60 because the bottom is going to go 60 feet up. The top has to go up only by 0. Now, all of this explanation is the hardest part. Calculating this is a piece of cake. I know everybody knows that. I mean, this is a basic, calculation you do. But I hope everybody understands how we arrive at it. And so Now, of course, this is 3/2 x squared from 0 to 60. You replace the x with 60. 60 squared is 3,600. You divide by 2, 1,800 times 3, 5,000 foot-pound. Now, the second part says, okay, what about if we want to lift only 25 feet? And I'm going to quickly approach it from the easy point of view, and then I'll give you the second one in a moment. And that is, if you cut this into two pieces, think about it as you want 25 feet up. So if you cut it into, let's say this is 25. Let me just use this. So let's say you have this top piece. So what do we have? 25 feet, class. So this is 25 feet. And then we have this bottom. Okay. I'm going to put a block around the bottom. Think about the bottom as one block. The whole thing, okay, has to move 25 feet, the bottom part. This, okay, this 35-foot block. The entire thing moves up by 25 feet. You can think of it as a fixed force, fixed weight. You can calculate the weight of the bottom 35, whatever it is, times the distance of 25, it's going to go up by 25 and you're done. However, what happens to the top? And that's important for everybody to see. The top portion, 25 feet, okay? That is a variable force because the top of it, let's say 1 foot away, it only goes 1 foot up, but the bottom of it goes 25 feet up. Do you see that? And it varies. Why varies? As you pull it up, this portion keeps on changing weight. The total weight of this portion is not constant. It changes due to the fact that the portion goes up. So that portion is by the integration. So the top 25 from 0 to 25, 3x dx. So we calculate exactly the same thing from 0 to 25. That is only the top portion, everybody. The bottom portion is fixed, 35 feet, okay? Times what? Times 3 pounds per foot. So times this would be the total weight, if you will. And then it goes up by how much? 25. In other words, the bottom part, you can think of it as a fixed part. Rho VD, and I'm going to really change this for you. By V, remember, we went to L class, okay? And now, what is the total? Add them up. Add them up. Add the two numbers up, and you're done. Add the two numbers up, and you're done. Here's a second approach. I'm not going to go over that, and evaluate it. I want you to evaluate it at home. The second approach is the following. Instead of taking the distance from the top, it changes to a point. Distance from the bottom is x now. Okay, first let's just, understand this, then we explain. So if the bottom is x, so what is this top now? 60 minus x. So the force is proportional to the remaining distance to the top. So the 60 minus x changes depending upon which portion you're putting up. So the dW that you had here, everybody, in essence works out here. The only change that you make, the x here becomes 60 minus x. And you can check it out. When you do that, you have to check your work. If you check it out at x equals 0, class, when x is 0, when the distance to the bottom is 0, that you're right here, okay? The force is 3 times 60 minus 0, which is 180 pounds. You're looking at the entire cable. What if at x equals 60, you're all the way up? So if you plug in, then there is nothing. You're completely up and it covers nothing and therefore no weight whatsoever. And you can evaluate the same thing, 3 times 60 minus x dx. From 0 to 60, that gives you part A. From 0 to 25 gives you part B. And I'd like you to try this on your own later on. Here's another example which is similar to what we just did. Okay, we're going to finish this section, class. A leaky 5-pound bucket is raised 20 feet. The rope weighs 0.08 pound per foot. The bucket starts with 2 gallons of water, and then it empties when it just reaches the top. Okay, so let's see what's going on here. I want to explain a couple of things. And again, there's a second method for this. I have put it at the bottom, at the end. You can look at it. What I want you to understand is this. If this bucket, okay, is 5-pound bucket, this has a fixed weight. It just goes up this much, 20 feet. So the bucket has a fixed weight, goes up by 20 feet. It's a simple case of FT. If the water was not leaking, everybody, the same thing, it goes up. You have to calculate that by 20 feet and you're done. The same thing for the rope. A lot of times they say the weight of the rope is negligible. If it's negligible, you don't have to worry about it. But notice what they say, the rope weighs what, 0.08 pound per foot. That density, that linear density, let me write next to it. The linear density we had to calculate, they have given it to us. Linear density of the rope. And so having said that, let's do a couple of things. Let's quickly look at this going from 0 to 20, okay? And so we have this distance of x. For the bucket is fixed, as I mentioned. For the bucket is fixed, everybody. Okay, for the bucket is fixed. And so just 5 times 20 is the answer. For the water, we need to look at the density, rho equals m over v, and 16 over 20 or 4 over 5 pound per foot. Okay. That's how the density works for the water. The whole weight of the water is 16 pounds. Okay. And again, we are looking at linear. So you really want to think about this as L, and this is the linear density, okay? Up and down, okay? Which means every foot, we have 4/5 of, 4/5 of a pound, 0.8 pound of water. That's the idea. If you multiply 0.8 by 20, you have total of 16 pounds. So please understand this times 20 feet gives us the total weight of 16 pounds. Okay. It's important to know if water is not leaking, and it is. If the water is not leaking, we just do exactly, this is, the weight is constant, and we do exactly like what we did with the bucket. Okay, everybody? We repeat the same thing with the bucket class. So we repeat the same thing, and that's simple, okay? But because it's leaking, you can't take it to be constant. So you just follow this concept that was explained before, small amount of water, okay, of length dx, pulls down with this force, 8 dx, okay, and let x be the distance. So this is delta x, okay, an increment, okay, of the rope or the water for that matter. The same concept is used. And let x be the distance this part has from the top. So x is this distance, okay. So this is x, everybody. So we're going to lift it by that much, okay. And so we are going to use the same thing that we had over there. Did I put 8 over there? Why did I put 8? My apologies. What color do I want to use? 4/5. Okay, everybody, 4/5. 4/5. Okay. All right. Let x be the distance. And now basically you calculate the integral of f of x dx from a to b, which means from 0 to 20. So the hardest part is to figure out this one, okay, class? This is a simple calculation, okay? So this is 4/5 times 1/2 x squared or 2/5 x squared from 0 to 20. You replace the x with 20, becomes 400. And you come up with the answer 160. The rope, we repeat the same thing, class. Now, class, we used 4/5 here, right? But over here for the rope, they give us the 0.08. Just use the given 0.08. So you've already done this, just replace this 4/5 with 0.08. Okay, same concept. Rho and the class, this is really the linear density. I mean, I should write. This is the linear density. Okay, and so you have the same thing. I don't want to, explain too much and waste too much time. Just change this to 0.08. Okay, because of the way the rope, weighs. And do the math. Plug in. You must add up this one, this one, and this one. They add up to the total. And as always, pay attention to the units, everybody. Pay attention to the units, okay? Okay. There's a second method that, I have put it for you at the end. And here's the last question. I want to spend a couple of minutes on that. How much work is done to pump the water out of this tank, which you have the dimensions, okay? So 10, okay. This is a cylindrical shape. The radius is 5, the height is 10, and then we take it up by 4 more, okay? What is the force? Is the weight of the water. Now, we've discussed that the density is 1,000 kilograms per cubic meters, or 62.5 pound per cubic feet. We've discussed that in the very beginning. That's a piece of information that must be given to you. Okay. So the idea is to move a slab of water, okay, a very small increment of the water, which we are going to give it the width of the x. We want to move it up. That's the idea. So if this distance at top is x again, how much are we moving it? X and then another 4 feet. So take a look at x, okay? This is how much it's going to move up, okay? So that's important to understand. Now, weight is density times the volume, okay? Rho equals m over v, okay? And v is pi r squared, okay? So because I see 4 feet and 5 feet and so forth, I'm going to use this one, class. So again, because I see that, I'm going to use this one. I have to use one of them. So both of them are given. Which one do we use? We use the one according to the units that we have to deal with. And so plug in, okay? We know the distance is x plus 4, and this is 62.5 pi r squared, okay? Where r is 5, everybody. I'm looking at this piece, okay? I'm looking at this piece. This piece, we are interested in finding the force or its weight. The weight is the density times the volume. The volume, we said it's a cylindrical shape, pi r squared. R is fixed at 5. Rho, we use one of those. We use this one because of the proper units. Now this one is 25 times 62.5 gives you this. We are moving this by how much? By x to bring it up here, and then another 4 feet to take it up there. So by x plus 4. And x plus 4 times that, and we have this increment of the work. In essence, this is dW, everybody. And so work is the same thing. This is the distance. This is the force, and the work, okay, from 0 to 10. The rest is easy. It's basic integration. I hope everybody is comfortable with all of this explanation from physics is the hardest part. I hope everybody is comfortable with that. This gives you 1/2 x squared. This gives you 4x, everything times this from 0 to 10. So this number is fixed. We keep it. This becomes 1/2 x squared. This becomes 4x, 0 to 10. And now plug in. Does take a little bit of a time. It's really not that big of a deal because 0 gives you just 0. So you plug in 10. Actually, it's not too bad. 100 divided by 2 is 50, and then 40. Now add them up, multiply by this. And just I would write the answer with pi first, and then we do the approximation. And as always, whenever you're dealing with application, you must write the units, everybody, or physics. Anytime you're dealing with units, please write them. Write the proper units, everybody. Write the proper units, always.